Okay, good. So let's start. So we have studied Chern classes. Chern classes are cohomology classes that one associates to complex vector bundles. And today I want to do something similar for real vector bundles, and we will discuss the so-called Pontryagin classes. And before actually going into Pontryagin classes, I need to make a few remarks about several constructions of bundles, or more precisely about several functors that one can apply to the fibers of a vector bundle. And so let's consider one which we have already discussed, namely the dualization functor. Dualization over the reals. So that is a functor going from n-dimensional real vector spaces, or a category of n-dimensional real vector spaces, to itself. It associates to such a vector space its dual space, and on the level of morphisms, or actually it's only defined on isomorphisms, such a morphism, isomorphism is mapped to f to the minus 1, so inverse of f dualized. Okay. And so this f to the minus 1 is needed to make it a covariant functor. And now, one thing that we observe is that, so we can, this is a C infinity suitable functor as we have discussed earlier. So we can apply this fiber-wise to vector bundles and get a new vector bundle. And the remark that I want to make is this, namely, if you do this, so if you have a bundle, F bullet, so a vector and R bundle and an n-dimensional real vector bundle, then and you apply this functor, and you get this new bundle, it's dual bundle. And what I want to emphasize is that these two bundles are actually always isomorphic. And why is that? Well, because what you can do is you choose a Riemannian metric on the bundle, a fiber-wise Euclidean scalar product, as one can choose a Riemannian metric on F as an auxiliary tool. On the bundle, let me call the metric G. And then we can write down the isomorphism, namely the isomorphism at the point x of the underlying manifold going from the fiber fx to fx star is defined as mapping an element in here to what? Now we need to get an element in here, a one form on the space, and for this we need the metric. So we take the metric at the point x, which is a scalar product on this space, and we insert this vector into one of the slots and leave the other slot open, which gives us a linear form. And that is a vector space isomorphism. In differential geometry, this is often called a musical isomorphism, or in physics, it's called lowering of indices. So this is an isomorphism, and if the metric depends smoothly on x, which one can arrange, then this will also depend smoothly on x in the sense that I made the definition. And so this is the isomorphism between these two bundles. So these two bundles are isomorphic. First of all. Secondly, we can do dualization also over complex numbers, of course. C. Then we start when we are working the category vector in C, so n-dimensional complex vector spaces. And we do pretty much the same thing. So to a complex vector space, we associate its dual space. And that's also the same definition here. And now the point is, this is no longer true in general. So bundles need no longer be isomorphic to their dual bundles. And in fact, we have seen examples already. Namely, an example would be take the tautological line bundle over CPN. And why is this an example? Well, we know what the Chern class is. So the Chern class of this bundle is 1 plus A, where A is this generator of second cohomology, represented by the Fubini-Studi form. Right. So that's the same notation as last time. And we know that the Chern class of the dual bundle is obtained from the Chern class of the original bundle by inserting signs at all the odd powers. So all those, I mean, they're all even degrees, but I take the degrees which are not divisible by 4. So in this case, this gives me 1 minus A. And so the Chern classes of these two bundles are different, and so therefore they cannot be isomorphic. So this is not equal, and therefore F is not isomorphic to X. So we have to be careful here. Okay, so that is the second remark. Now, third remark. We can also do a different thing for complex vector spaces, and that's complex conjugation. This also gives me a functor going from n-dimensional vector spaces to n-dimensional vector spaces. And here, the space F gets mapped to the complex conjugate. Now, what's the complex conjugate? If you have an n-dimensional complex vector space, then the complex conjugate is, as a set, it's the same space. It's the same as F. And in fact, as a real vector space, it's the same thing. So addition is defined here the same as there, and also multiplication with real scalars is defined the same way here and there. It's just that the multiplication by the number I, which is changed. And so that means, so here we have F bar equals F as an R vector space, and the multiplication with complex numbers gets modified and to a new one, and A times V, so A complex number, V an element in the vector space, gets replaced, so that is in F, by A star V, let's say, in the equation, which is defined as A conjugate times. So the multiplication by I is replaced by minus its multiplication. And this is an abstract construction that you can perform, and this is the conjugate space. What happens to morphism? Well, morphisms do not get modified, because if F is linear, a linear map from F to some other space, then it will also be linear from F bar to the bar of the other space. Because, see, we have F A star V. By definition, this is F A conjugate V. F is linear in the usual sense, so this is A conjugate F V, which by definition is A star F V. Right? So, if the map is linear for the original, or as a map from F to G, then it's also linear as a map from F bar to G bar. Good. Okay, so that's this functor. And that's conjugation. And now what I claim is that in order to bring this, connect this to dualization, so F star is in general not isomorphic to F, but it's always isomorphic to F conjugate. So that's also a smooth functor, obviously, because this map as a map from GLN to GLN is obviously smooth. And so F star is conjugate, is the isomorphic to F conjugate. And the argument is now similar as here because one can choose an emission metric on F using a partition of unity. Let me call this emission metric H. And now the isomorphism is pretty much the same. Psi x going from F var x to F star x is defined by mapping B to H at x of same thing. So my convention here is the Hermitian scalar product is linear in the first argument and anti-linear in the second argument. Since it's linear in the first argument, this thing is really in linear form. So it really is an element in here, right? And since it's anti-linear in the second argument, this map is a linear map as a map from F conjugate to that map. So that's the reason. So these Hermitian scalar products are linear only in one slot and anti-linear in the other slot. And this is why we have this isomorphism. But apart from that, now it's the same situation as in the real case. Okay, good. So this was the third functor. There are two more. Namely, the next one is realification. So this is a functor from complex spaces to real spaces, or twice the dimension, where F gets mapped to F R, and in fact, this is exactly the same thing as that one, and as a set and also as a real vector space, and we just forget the complex multiplication. So forgetting complex multiplication, only keeping real multiplication. And morphisms also get mapped to themselves. Now, because if something is complex linear, then it's certainly also real linear. And that's a C infinity suitable functor, so we can apply this to fiberwise to a bundle, because that's C infinity suitable. Because, well, what do we have to check? If we have a map from something, a smooth family, or a map from some space into the structure group of the original left NC bundle, then, and we apply the functor, then we must again get something smooth. But that's in this case clear. The structure group of this one is GL and C. The structure group of that one is GL2 and R. And applying this functor is just, for the transition functions, it just means that we include here. And that's sort of a smooth map. This inclusion is smooth. No problem. Good. So that's one thing. And finally, the last functor that I want to discuss, you can probably already guess what it will be. So what's your guess? Complexification, yes, of course. complexification. So that's the last one. So this goes in the opposite direction. We start with a real space and associate to it a complex vector space of the same dimension, complex dimension, so twice the real dimension. And here the space, which is a real vector space, gets mapped to this space tensored with complex numbers over the reals. Right, so F is a real vector space, the complex numbers are a two-dimensional real vector space. So I can form this tensor product, and then this is at first a real vector space again, but now I also have a complex multiplication, because when I have a complex number, I can just multiply it on the second factor. So this way, I obtain a complex vector space. And yeah, on the level of morphisms, then you just extend this complex linearly, so you map F to, in this product, just to F tensor the identity. Now again, this is a C infinity suitable functor, so you can do this fiber-wise. Because our transition functions here take values in GL and R, and here they take values in GL and C. And applying the functor just means that you look at this in A. And that's of course also C. Okay. So we have that, and now let's see what happens if we compose these two last functors. Okay, so let's start with something complex. Let's first realify so that F be a complex vector space. And then, so we can first realify and then complexify again. In fact, this is usually often also abbreviated as FC. That's application. And so what we have is this. Question, how does it relate to the original complex vector space F? Well, okay. What I'm claiming is that this is canonically isomorphic to the original. So that's an n-dimensional complex vector space. That's a 2n-dimensional real vector space. So this is a 2n-dimensional complex vector space. So it can certainly not be equal to F because this has only half the dimension. But what we get is indeed this. It's canonically isomorphic to F plus its conjugate. And what is the isomorphism? Well, here the elements are linear combinations of elements in Fr, which as a set is the same as F. So this V can be an arbitrary element of F tensor, and here we then tensor with complex numbers. So here we can have some element in the complex numbers. So all elements in here are linear combinations of those. And what I'm doing is I mapped this to, since for this construction we don't need the complex structure on F, but we still have it. We start with a complex vector space. So what I can do is I can just multiply Z onto V, remembering the original complex structure of F. And I can also do the same thing with Z conjugate. And now let's see. This is, so that's a map between, so let's first look at it, let's say, as a real linear map, certainly a real linear map. and the two spaces have equal dimension. So what happens if something like this maps to 0? Well, if something like this maps to 0, then this would be 0, and then z or v would be 0, and the tensor product would be 0. So this is shows, actually you would have to do the argument with linear combinations of those, really. But it's an injective map, and by dimensional reasons, it's a bijective map. But it's also complex linear, and that makes it a complex isomorphism, namely, complex, if I multiply this thing with a complex number, what I have to do is I have to multiply this slot with my complex number. That was the definition of the complex structure here. So I have to multiply the z with the complex number. So that means the first slot gets multiplied with that complex number, and the second slot gets multiplied with its conjugate, which is the complex structure for f bar. So this shows that as a map from here to there, it's also a complex linear map. So that sets up the isomorphism. Now, the other way around, let F be a vector space over the reals. Let's first complexify. And now, let's realify again, meaning we forget the complex structure. So the complex multiplication is only in this part. So forgetting the complex structure in C means I have to replace C by R2. So then this gets mapped to F tensor on R with R2. And this is obviously canonically isomorphic as a real vector space to F tensor R over R, but that's just F plus the same thing again. So I just get 2 copies. Alright, so and for bundles here, this means if I have a bundle and I first realify it and then complexify it, then this is isomorphic to the bundle F plus its conjugate. And here this means if I start with something real, this means if I first complexify, then realify, and this is isomorphic to this original bundle plus itself. So this is just something to keep in mind. Alright. Now after this introduction to algebraic formalities, let's start with Pontryagin tasks. So what can we do if we have a real vector bundle? Let F be a real vector bundle, some rank. We know how to treat complex vector bundles, so why not just complexify it and take its Chern class? And that's basically what we will do, essentially. But then we have to make an observation first. So if we complexify, then I'm claiming, since we started with a real bundle, we know that the bundle is isomorphic to its dual bundle, because it's real. But if we now complexify, then this will give us that this is also true for the complexification. Because it doesn't matter whether we first take the dual and then complexify, or first take the complexification and then the dual. This you can check. So here we are in a situation which is not always the case for complex bundles, namely that it is actually isomorphic to its dual bundle. This is because it's not an arbitrary complex bundle, but it's because it's a complexification of a real bundle. This already also tells us that, for instance, the tautological bundle over CPN cannot be the complexification of a real bundle. Anyway, so we have that, and then we know that if we take Chern classes of this complexification, then the Chern class of F, complexification of F, is the same as the Chern class of the complexification of its dual. But we know that this is the same as the Chern class of the original bundle up to a sign, namely the sign -1j. And we see that this tells us that the Chern classes for odd j must vanish. Therefore, Cj of this bundle is actually 0 if for odd j. It doesn't tell us anything about the Chern class for even j, but for odd j, it has to vanish. Okay. So, but that's how it is. And now let's make a definition. Namely, Pj of F, my real bundle, on M, so let me call the base manifold M, which I define as, so there's no need to look at these odd classes. So those are for J odd. So I only look at the ones for even index. So I take the Chern class of degree 2j of the complexification. And it's a tradition, would not be necessary, but it's a tradition to have an alternating sign here. So let's stick to this convention. Now, in which cohomology of my base manifold M is this guy sitting? So what do I have to write here? 4j. Namely 2 times 2j. Exactly. So now we have things only divisible in degrees, something sitting in degrees divisible by 4, because the other even degrees get 0 anyway. Alright, and these cohomology classes, so this Pj is called the jth Pontryagin class of the bundle F. And if I take add them together, I'll take 1 in degree 0 plus 1 in degree 4, and so on. So that's now sitting in the cohomology, the even cohomology, but it's actually sitting in the cohomologies of the degrees divisible by 4. So this is the total Pontryagin class. All right, so that's the Pontryagin classes. And this essentially gives us all the characteristic classes that one can define for real bundles, except for one which we will discuss later. So it's pretty convenient because they can simply be derived from Chern classes. And let's see, so some examples maybe. So, example, if my manifold is Sn and my bundle is its tangent bundle. So, what is the Pontryagin class in this case? Well, yeah, there's probably not much interesting happening here because you remember that the tangent bundle of the sphere is not in general trivial, but we don't know that yet. But it's always stably trivial. So what we remember is that this, if I add the normal bundle in Rn plus 1, then I get the bundle of Rn plus 1, which is trivial. So I get this one. So the bundle is stably trivial. And this is as real bundles. Now if I complexify, then the complexification is of course, I have a one-dimensional trivial complex bundle here. Then this persists. And if I now take Chern classes, this tells me that the Chern class of T of the tangent bundle, so here plus trivial bundle here, gives me the Chern class of that trivial bundle. But trivial bundles have trivial Chern class, and by this formula of Chern classes for sums, we have that this is the Chern class of TSN C multiplied with the Chern class of the trivial bundle, and this is trivial, this is just one, so I get the Chern class of the sphere. So the Chern class of the complexification of the tangent bundle of the sphere is trivial. And then of course the Pontryagin class is also trivial. Okay, so this is so we cannot capture anything non-trivial on the sphere with this class, but maybe we have better luck on complex projective space, because we already saw that the Chern class of this complex tangent bundle is non-trivial. So let's see what we get. Complex projective space. That's a second example. So here I want to look at this as complex, complex projective space. I want to consider it as a differentiable manifold, not as a complex manifold. And so in this sense, this tangent bundle is a real vector bundle. However, we know that it's a complex manifold, so this tangent bundle does carry a complex structure, and therefore the complexification, if you complexify this, we look at this as a real vector bundle, then as we have just discussed, this gives me the tangent bundle of CPN as a complex bundle plus its conjugate. So here I consider it as a real bundle, 2R bundle, and here these two things are considered as vect and C bundles. Now, after complexification, this is of course also a vect and C bundle, vect 2 and C bundle. So what does this tell us about the Chern class? Well, the Chern class of this thing is the same thing as the Chern class of this sum, and so it's the product of these two Chern classes. So it's the Chern class of this one and has a complex bundle multiplied with the Chern class of its conjugate. And this guy we've computed. So we saw that this one gives is given to us as 1 plus a to the n plus first power. 1 minus a. get here? Well, for this one, we have to flip signs for all odd indices. A has the index 1, yeah. So flipping signs in all odd indices is the same thing as replacing A by its negative. So this would give me 1 plus A to the index first power. In other words, we get, combine this is 1 minus A squared to the index first power. And we can expand this in terms of a polynomial series. So then we have summation from k equals 0 to, we'll see, let's say n plus 1. Then here we have n plus 1 choose k times, and here we have minus a squared to k's power. Right? But now let's see. The maximal power that can actually occur is the one when the degree is equal to the dimension of the manifold. The dimension of the manifold, the complex dimension is n, the real dimension is 2n, A has degree 2, so the whole thing has degree 4, and to the power k it has degree 4k, so we get something not trivial only if 4k is less than or equal to 2n. Right, 2n is the real dimension and 4k is the degree of this form. And so we only need to sum all the way up to k being the bottom of n, so the largest integer small or equal to n. All higher powers give us 0 anyway in the homology. So that's what we get for the Chern class. And for the Pontryagin class, TCPN, n over 2, yes. Okay, so for the Pontryagin class we have to do one more thing, right? So it's not exactly the Chern class of the complexification. We have this additional sign flipping here. So that means in degree 0 there's no sign flipping, in degree 4 there is a sign, in degree 8 is none, etc. So what does this mean for our power series here? Well, this means for even k there is no sign flipping, and for odd k there is a sign flipping. But for odd k, that's when we have a sign. So the sign flipping just removes this sign. So that's what we get on Pontryagin class. So let's look at a few examples. So CP1, if we just apply this formula, here n is equal to 1, then this is 0, so there's only one summand, which is just a constant term. Then the Pontryagin class, that's the 2-sphere. Right? So for CP2, in this case n is equal to 2, so there's 2 summands. So the first one for k equals 0 always gives me a 1. Then I have 1 here, and this is also a 1, so I have a 1. And then I also have to put in k equals 1, n plus 1 choose 1 is n plus 1 times a squared. Now the Pontryagin class of CP3, 6-dimensional manifold, 1 plus, now again, so we have 3 on 2 here, so bottom is 1, so we have 2 summands only, k equals 0 and k equals 1. And then here we have to take 3 plus 1 is 4, choose 1 is 4, oh, I forgot the 3, this is 3, this gives me 4 times a squared, and nothing higher, etc. And in case of CP4, then there would also be an a to the cubed term. Yeah, a to the a to the power a to the fourth power, corresponding to k equals 2. Yes, it's a complex manifold. All complex manifolds are orientable because the complex multiplication induces an orientation. And in fact, the Fubini-Studi form is a symplectic form which induces an orientation. But I mean, I'm not assuming, so for this theory of Pontryagin classes, it's not assumed that the bundle is not relevant in this case. It will, however, be relevant later. Okay, so this is for the Pontryagin class. I should summarize the properties of the Pontryagin class. So let me call this theorem, although it's not very deep. Namely, the Pontryagin class. So I have to finish this properly first. The Pontryagin class has the following properties. First of all, it's natural. Naturality, meaning that if f from n to f is smooth, then if I pull back a bundle along f and take its Pontryagin class, then that is the same thing as the pull-out. Secondly, it has this additive formula, well, the Pontryagin class of two bundles, f1 plus f2. And the same as the product of the Pontryagin classes. Thirdly, if f1 is isomorphic as a real bundle to f2, then the Pontryagin classes coincide. And lastly, if f is trivial, then the Pontryagin class is also trivial. So let's see. Proof. And well, actually, slots A, C, and D follow directly from the corresponding properties of the Chern class. Because the Chern classes are natural, and complexification and pulling back commute. And so, from the naturality of Chern classes, we directly get the first one. Similarly, if two bundles are real bundles are isomorphic, then their complexifications are complex isomorphic, by just complexifying the isomorphism. And therefore the Chern classes agree, and therefore the Pontryagin classes of the original bundle agree, and similarly for the last one. So A, C, and D follow directly from the corresponding properties of Chern classes. In B, we have to be a little bit careful because of the sign flip. So we have to check that we did not mess up the sign flip. But this probably that the sign flip doesn't mess this up. So let's see. All right. Yeah. Well. What do we have? So if you first look at the Chern class, the complexifications, then we do have this property, as we know. Now, if we fix a particular degree, what does this tell us? Well, the jth Chern class of this bundle obtained. And now I cannot just say it's a Chern case thing here times case the J thing here. That's nonsense. So because in this multiplication the degrees add up, so I have to take all possible combinations here and here that add up to the correct degree. So let me write it like this. This is from k equals 0 to j. I take this case Chern class here times the j minus case Chern class of the other one. Right? And now let's see what happens if we pass to Pontryagin classes. For Pontryagin classes, we only need to consider the case where the j is even, right? So if we restrict to the case of an even degree here, then, right, I could write this also as, let me write this like slightly differently, namely as C, what is it, K and L, such that K plus L is equal to J. Prefer that one. Now we have, if we restrict to integer, then now we have K plus L equals 2J, C K of the complexification times CL of the complexification. But these two bonds are also complexifications, so we know that if one of these indices is odd, then the thing is 0 anyway. So also for these terms, we only need to consider the case where K is even and L is also even, because otherwise it's 0. So we can also write this as a 2K and a 2L, so that I have 2K plus 2L equals 2J. And then I can remove the 2's again, right? Okay. So we have this formula. Good. And now, this is really, we know that this is the same thing as minus 1 jth power of the corresponding eigenclass, sum. And this one is sum k plus L equals j of, here we have a sign minus 1 k, k's Pontryagin class, times, and here we have minus 1 to the Lth power times the corresponding Pontryagin class. And now k plus L is equal to j, so I can also push this out and I get a minus 1 to the k plus L, which is j. It's no complexification anymore, that's correct. Here it's still complexification, and here it's no longer complexification. Yes. Thanks. And so we see the sign is the same as here, so it just drops out. And therefore, this formula still holds without any problems. But that's only because the odd parts in the Chern class vanished. But only because of that. Right. Good. But this means we can basically compute with Pontryagin classes exactly the same way as we can compute with Chern classes. It's the same computation. Good. And now let me come to additive and multiplicative classes. So I'm going to explain a procedure on how to build classes out of Chern classes, for instance, or Pontryagin classes, to get to new classes, and these new classes come up in applications. This is why it's important. Additive and multiplicative classes. Okay. I'm going to start with additive classes. And I'm going to do this in a rather algebraic way to start with. So let K again be reals or complex complex numbers, and so that we will be able to, yeah, anyway, I could do it actually over any field of characteristic 0, wouldn't matter. So let me fix that, and let R be, maybe I hold it, let A be a graded commutative algebra, or rather commutative graded algebra, I should say. That means A0 plus A1 plus maybe infinite dimensional. Let this be a commutative graded K algebra. So what does that mean? So it's it's a K algebra. So it's a K vector space, and this is a vector space decomposition here. So all these A's, A0, A1, etc., are this K vector spaces. It's an algebra, so we have multiplication. It's a graded algebra. This means that if I take something from AI and multiply it with something from AJ, then I get something AJ plus J. So it's a degree, like the degree for forms of homology classes. And it's commutative, meaning that really commutative in traditional sense. So A times B is equal to B times A. It's not. You also have this concept of graded commutative, which would introduce a sign depending on the parities of these adjacent. That's not what I mean, right? So I mean really commutative in the traditional sense. That's why I wrote commutative graded K algebra and not graded commutative K algebra. Okay, and now fix a natural number. So later this will be the degree, the rank of a bundle later. Could also be 0, but then it would not be interesting. But anyway, and so let me and a power series, a formal power series in one variable. So that should be an element in formal power series. I usually note it like this, similar to polynomials, except that you have these two things here to indicate this is not a polynomial, but this expression is only finite, but it's a formal power series. So it's something like G0 plus G1 times X plus G2 times X squared plus etc. And it doesn't have to end. And there is no convergence discussion here, so it's just a formal expression. So essentially, it's the same thing as the sequence of the G's, of these coefficients. But writing it as a formal power series also immediately gives me a multiplication, because I know how to multiply a power series. So so this is also an algebra, infinite dimensional algebra. Okay. So let's fix one such power series. And well, associated with this number n and this power series, I can write down a linear isomorphism of my algebra as follows. Let me define lambda G. So linear, not an algebra, but a linear map from A to A by. So it will preserve this grading. So AJ will always again be mapped into AJ. The degrees are preserved. And what does it do? Well, if I restrict to AJ, then it's a multiple of the identity simply. Identity of AJ. But the coefficient depends on J. And in fact, it depends on these coefficients in the power series. Maybe to restrict going to the case where I have the 1 here. Sorry. So here it starts with a 1. This makes sure that it's an invertible power series. It can be formally inverted in the algebra power series. But anyway, so what do we do here? Well, we take the following multiple of the identity, namely gj up to a sign, -1 to j plus 1, and then in addition I multiply with j. The sign is -1 to j plus 1 times j times gj times the identity. This is for j at least 1, and in degree 0 I use this number n as my multiple. So in a moment. Okay, so for this lambda, this is true for all j's. But now, so that's just an auxiliary linear map from my algebra to my algebra. And now I want to actually write down the concept for that gives me my additive classes, namely if C being 1 plus C1 plus C2, etc., an element in A, and I'm writing C so that we may think of Chern classes already, where this A is then the cohomology, the even cohomology algebra of the manifold. And so if we have such an element, so what we do is this. We take this and apply the logarithm to it. So what does that mean? So here I use the power series of the logarithm, which we know is given as sum from k 0 to infinity. And then what we have, alternating sums. No, we have no. This one is k plus 1 to the k on k, and this starts at 1. So this is the logarithm series. So, okay, so I have this. This is again a formal power series. I want to insert this element into it. So what does that mean? So this element C is of the form 1 plus something, and if I take this power series, I have 1 plus something, and then this means I have to take certain powers of the something and add them up. Now the something is now the sum of C1 plus C2, etc., and so forth. And you may wonder, is there a convergence issue here? But there is no convergence issue, because this is supposed to give me again an element in A, and if you take the result of this in any given degree, then only those elements here where k is at most that degree enter into it. So in each given degree, each component of the result of the logarithm of C is actually a finite algebraic expression in finitely many of these components. Because as soon as you have a too high power here in this expansion, then this will only contribute to higher degrees. I mean, the higher the degree of this thing you take, the bigger part of the C you need, but always only finitely many. So there's no question about convergence here. So this is always defined. Okay, so that is an element in A. Then I apply this linear map to it. I get another element in A. And but this has things only in a degree at most 1, right? So this starts with the first, also this starts with an element in A1. So there's no contribution to A0 from this. And the contribution in A0 I do put in by hand. by just multiplying the thing with, if I take 1 here, then it's just n times 1 plus. So A0 should contain the unit outside. So it's a graded algebra with unit. And the unit must sit in A0 because of this relation here. All right. Good. So this transformation that takes C and spits out a new element, or this one, put this one, and this is again an element A. So in degree 0 it just multiplies by n, and in higher degrees is this complicated thing. And we will see in a moment why this is reasonable. Okay. Definition. Let C equal to C of F be a Chern class of a complex vector bundle, so vect n C bundle on n of rank n. Then this element when I apply this to the Chern class, and where my algebra is now the even cohomology algebra, so that's even cohomology algebra of space manifold. This is called the additive class of F with respect to the power series G. Okay, this. So what can we directly read off from this definition? Well, one thing certainly is that it's definitely a characteristic class in the sense that it's natural. We certainly have this name, let me call this GC of F. As an abbreviation. Then certainly we have the GC of the pullback of a bundle is the same thing as the pullback of the GC bundle. Because this holds for any individual Chern class, and so it holds also for any product of these Chern classes, any sums, any combinations. So no matter how this algebraic procedure works exactly, in any case, each component of GC is a certain polynomial in the Chern classes of the bundle, and therefore this is still true because it holds for Chern classes. Okay, so we have that. So this naturality is not a problem. And now let's see why I'm calling this an additive class. All right, I told you this is called the additive class of the bundle with respect to the power series. And how is that? Well, if you look at the sum of two bundles, F1 plus F2, what will happen? So this is then Okay, so we have the rank of this one, the ranks add up. So we have the rank n1 is the rank of f1, n2 is the rank of f2, let's say. So we have that times the one here, homology algebra, plus g, and now we have the logarithm of the Chern class of the sum. But here we can use this property for Chern class, that this gives us the Chern class of the first bundle times the Chern class of the second bundle. Right. And now we use the properties of logarithm, which tells me that I have n1 plus n2 times 1 plus g, and this logarithm turns products into sums. The logarithm turns products into sums. Now this lambda is linear, so we can take the lambda to the first thing and look at, combine this with n1. This gives me gc of f1, and the other part gives me gc of f2. So we have that. So unlike Chern classes, which give me the product when I take the sum of two bundles, these additive classes just preserve sums in this manner. That's why they are called additive classes. And that's the reason for using the logarithm in this definition. Good. So let's look at an example. In fact, so as a power series, I want to take the exponential series. Well, that's one of our favorite power series, certainly. So that's the exponential series. So we have this decomposition, and these are just the parts of homogeneity degree J, if you like. And now, if you compute this term, so like if you compute the logarithm, I tried to explain it earlier, but maybe I didn't make it very clear. So for this, in order for this to define an element in A, I need to define its components in each AJ. Now, how do I get a component in each AJ? Well, I insert this element formally into the logarithm according to this sum, or to this power series. And in order to get, so this the y is now mixed, has mixed degrees. Y is equal to C1 plus C2, etc. And I insert this here, and then I expand all the powers here, which give me then certain expressions in these C1, C2, etc., and add all this up. And the part in degree J for fixed J only sees terms for which the K is at most J, because we start with something of degree 1. So the Kth power of C, of Y, which is this sum, has all the parts have at least degree K. Therefore, in this infinite sum, only the terms where K is not larger than J enter into the part of homogeneity degree J, and which is a finite expression. Well, okay, doesn't really matter, right? So he's asking whether this is a sum or a product. Yes. So do we allow infinite terms or do we allow finite terms? Okay, so maybe that's the question. Yeah, and in our case it doesn't make a difference because we will be treating homology algebras, which are finite dimensional anyway. And so there are actually only finite many parts, and there is no difference between sum and product. In general, yes, he is right in the sense that Even if C has only finitely many parts, the logarithm of C will have infinitely many parts. So this will not be an element of the sum, but rather of the product. That's true. So to avoid this discussion, let me just add finite dimension. Then I don't have to worry about it. Because this is where we will apply it anyway. Otherwise, I could work with the direct product instead, and this would work as well. Yeah, good point. All right, now we come to the exponential series. Good. So what do we have here? So let's see what we get. So if we have, so in order to compute the corresponding additive characteristic class, we have to look at the logarithm of the Chern class of a bundle. So C is now the Chern class of some bundle. And my algebra is the cohomology algebra of the underlying manifold. So then, yeah, so what we get is logarithm of 1 plus C1 plus C2, etc. And it's actually finite. But I don't care where it ends. And now we put this into this power series. This power series. So we start with k equals 1, where there is no sign. And then I have just to take C1 plus C2 and so on, divided by 1. So that's the term k equals 1. So then we have the term with k equals 2. There is a sign now. And then we have to take this element and square it and divide by 2, plus higher terms. Right? The next term is of degree that is 3, etc. Okay, so what do we have? So this lies in A1, C1. So and here this part also lies in A1, but it's already squared, and that one lies already in A2. And the higher parts are even higher parts. So there is no other contribution to the A1 part except for this one. None from here, and also none from the following terms, because they are, so that term is at least of degree 2, the next one is at least of degree 3, etc. So that's the only contribution from in degree 1. Now what we get in degree 2, we have something from here, that we see 2. But we also have something from here, namely we have C1 squared. All other terms, if I expand this, are of higher degree. But I have a C1 squared on 2 term. And the remaining terms are at least of degree 3, etc. So that's my degree 2 part. Plus higher terms. Which in principle we could expand as far as we want to go. Good. And well, so that's the logarithm. And now I'll have to insert this into, so far the power series has not entered, the exponential series. But the power series enters when I now apply this lambda to it. So lambda of this particular power series applied to logarithm of C. So let's see. What does it do in degree 1? In degree 1, j is equal to 1, no sign. J is equal to 1, doesn't matter. I have to take g1 in the power series. And my power series is the exponential series, so the coefficient is 1. So it's just the identity, right? So I get here it acts as an identity. What does it do in degree 2? In degree 2, j is equal to 2, so I have a sign. I have to multiply by 2 and take the coefficient from the exponential series. This coefficient is 1/2. Multiplied with 2 is give me just 1, but I have to the sign, which is a -1. So I have minus this term plus higher terms. That's what you get. And in order to get the actual series, then I have also this zero order term, which depends on the rank of the bundle. So then GC of my bundle is then the rank of the bundle times 1, which might be something, some n. And then I have C1, the first Chern class of the bundle. So that is the H0 part. That is the H2 part. Plus, and here I have C2 of F minus C1 of F squared on 2. So that is the H4 part plus higher terms. Oh, I forgot the minus sign. This minus sign. Yeah. Now this came from this minus, right? So this is that. And this thing, this particular additive class, is a famous class. It's called the Chern character. Definition G is here for the power series, the exponential series, the class GC of F, which one then writes as CH F, is called the Chern character, not the Chern class, but it's called the Chern character. Okay, so maybe I'll leave it at that. Next time I will keep continuing this and on Thursday, and also introduce multiplicative classes. But of course you can apply this procedure not just to Chern classes, but equally well to Pontryagin classes if you want to do it work in the real world. However, so the Chern character really is the one important additive class for complex bundles. And it comes up in index theory, etc. I will come back to this later. So thank you.